Next, we have Jeff Cooke from Swinburne talking about a Roman program for very fast transients.
Thanks, appreciate that. I'm not able to pin that timer, so I'll just do my best here. Okay, so I'm progressing from very slow to faster to the fastest transients. Nice segue. I'll be talking about a program for very fast transients. And this is a collaboration with people here, July Zhang, who you heard talk from yesterday at Swinburne, Simon Driver at University of Western Australia, Uma Rava-Prograda, Jason Rhodes, and Eric Huff at JPL, and help from a number of other people. And I want to say that, here's the famous footprint of Roman. And, I see that, and I keep thinking it reminds me of something. I just can't picture what it is. And I think it is the Space Invaders, right? So maybe it's just me, but it kind of has that look. And, maybe if I can get past the trademark, that could be our program logo. Okay, enough of that. All right, let's move to fast transients. Okay, so for fast transients, I'm talking here millisecond to a day, approximately long, maybe a couple days. And so we know of a lot of transients in this space. At high energy, there are a lot of transients shown here in one of these characteristic timescale versus luminosity plots. And this is for the X-ray. And these exist also in the radio, basically at in many wavelengths. And in the radio here, this x-axis is seconds, essentially log seconds, if you're observing at 8 gigahertz. And so there are a lot of fast transients in that space. And if we look at the optical wavelengths, this area we're exploring now, to the right there are the conventional transients that Ryan just talked about, and even in Ori with the superluminous supernovae. And to the left here are these fast transients. And we know of things like gamma ray burst afterglows, et cetera, and things that are in this space. And over the last few years, there have been other classes identified, serendipitously, whatever. So the space is filling up as technology improves, and we're trying to explore this space to the fastest part here. And there are many theorized objects and things here. So we're trying to, because nature is filling up this space, is there an end or not? So we're searching for that. And this particular plot is for the optical. But in the infrared, it kind of looks like this. And so we really want to explore this space with Roman. And so why Roman? Well, as mentioned, it's essentially an unexplored field, an area. And this line here, if history has taught us anything, it's that nature surprises us when we develop new instrument capability. And so we have deep, wide field infrared. And so that's going to open up this new area. And so fast transients are rare, so you have to probe a large volume, large cosmological volume. So you need a wide field. They're fast, so you need very fast exposures to sample them. And when you do very fast exposures, they're necessarily shallow. So you need a very sensitive wide field instrument. And then from space is nice because things like the atmosphere and hinders it a little, and you need very deep imaging to get extragalactic transients and very early detections of slower evolving events. There's also other advantages like the high resolution to enable the location of these things in tidal tails or what have you, and that there is very little data in the IR for many classes of known transients, even variables for that matter. And so the true transient rate needs to be explored in the infrared. Sorry, it's early in the morning here. I apologize. Okay, so for the science, what kind of things are we looking at? Well, there's all kinds of things. There are theorized events, known events, and on different timescales. And of course, many of these are dust obscured. And so that'll be probed in this with this program. And we'll be going for the fastest events and then for early detection and fast timescale monitoring of slower evolving events. And if coordinated with other telescopes, it's very powerful because then you can understand the infrared contribution to all of these other types of explosions that are listed here. I'm not going to go through them, but there are a whole number of fast explosions. And so two things we want to capitalize on with this program, and one is the fact that one of the receivers for the data for Roman is in New Norcia in Western Australia, and that it be linked to the POSI supercomputer that we'll be using for processing this. And also we're going to be banking or using the infrastructure already built up from the Deepwater Faster program here's just a slide on that. It's a program that coordinates over 80 telescopes on every continent in space, as shown here, at all wavelengths, radio through gamma ray, and including particle detectors. And the basic concept is to coordinate, about 10 or so of these at every wavelength. They're wide field instruments, point them at the same field, at the same time, take fast cadence observations. When fast transients go off, you have all the information you can get before they fade away. But if they're a little bit longer, you can use real-time, we have real-time data processing and identification to then trigger rapid response spectroscopy and imaging from different wavelengths from high energy to radio. And we also monitor the fields later, because some fast transients are associated with slower duration events, like supernova shock breakouts, for example. So anyhow, there's 3 different modes that we are thinking about for this program. One is a very basic mode where we take data from some program or a geo program that takes fast cadence images over several hours and ideally over several days. And those data are collected by the program or ourselves, processed in the normal way, in some 48 hours later, whenever the processing gets done. And we just look at the data to make some light curve classifications and rates. So there's some science to be done there, but it's limited. And here's just kind of a pictorial of that. So there's Roman, the data goes down to New Norcia and gets processed, and you get light curves. The second mode is taking that, but then adding the coordinated telescopes at other wavelengths. And so they would shadow Roman where it's pointing at the time, and those data would be processed most in real time, but at some point. And then they're cross-matched later with this data that come processed later from Roman. And in that case, you can get some multi-wavelength light curves like shown here. So you have the first thing that I showed you, Roman will be processing, and you add these other facilities to produce multi-wavelength light curves. And here, and listed there are some facilities there that we've used with deepwater faster program in the past and would use in the future. And I just want to highlight one of those things, which is a Keck wide field imager. It's an instrument that I'm leading for Keck. It's a 1 degree wide field imager, optical imager, blue sensitive, and it can reach extreme depths like 29th, 30th magnitude, and is a perfect complement for Roman science in transients and even beyond. So it's expected to be online at the same, beyond sky about the same time as Roman. Another talk for another day, but if you have questions, let me know. Okay, the third mode here is to then build further on this. So we've got the data taken by Roman, we've got coordinated telescopes, and now if we can process those data very fast, and that's what we're putting most of our time into, we can actually trigger telescopes on these fast transients before they fade. And so what we want to do is take advantage of this 4-hour pass over New Norcia. We're just taking the data as Roman data is coming in, and intercept those data from the receiver and process them in real time along with the real-time processing of the other wavelength data, run them through identification, and then trigger telescopes onto those to get some information. And here's a pictorial of that. So the Roman data will then go straight into the supercomputers at Pawsey and All-Star at Swinburne. All the other wavelength telescope data will also be coming in, and they'll get processed together, analyzed by our team in the mission control room at Swinburne here, and then trigger telescopes accordingly, anywhere from high energy optical to low energy. And that way you can get redshifts and spectral information, etc. And so if we apply this to some existing programs, there's the supernova survey up in the upper left there, kind of gives you a sense of what the images are, depths, or the times on them. But it's inconsistently mapped, right? They're going around mapping and then they come back around. It saves slew time, but it's poor sampling for this type of work. And so because of that poor cadence and poor sampling, it's not like evenly sampled. You can only get a few of these types of transients that from the big list that I showed you, the ones that are in the darker color. And if we look at the microlensing survey, now that has a really good cadence and it kind of goes over and over 7 tiles, really nicely set up for this. However, it's pointing at the galaxy, which has got high extinction. And so because of that, transients that need optical or UV, it's difficult to go deep and more difficult in general. So some of those are not going to be covered with that type of survey. So in the end, a program or a geo prompted by us would have a 1-minute consistent cadence over over the 4-hour pass over 7 days, consecutive days. And those consecutive days matter because you can confirm that it's a fast transient. You can see how it evolves, especially if it's an early detection of a slower evolving event, et cetera. And so if we have that kind of cadence, we can get almost all of these transients. So that's the idea. It's to use the wide field, deep sensitivity of Roman to explore this new regime of fast infrared transients and to understand or catch slower transients early and to understand their true rates. This was kind of the points I put up earlier. So this particular program capitalizes on the New North Sea Observatory in Australia, which can be connected to supercomputers and our network and the radio telescopes in particular in Australia for things like fast radio bursts, et cetera. And it builds on our DWF program, the Observing Approach 1 that I showed you, that first pass. We'll get some light curves, but it can't really classify many, and you don't get any redshifts or spectral information or physics. When you coordinate other telescopes, you do get more insight into physics, and you can classify some better, but still you don't have much spectral information. Being able to intercept those data and doing it fastly lets us do all of this. And I'll leave it there. Thank you very much.
Thanks, Jeff. If there are any questions, please feel free to put in the Slack or chat. This definitely seems like the Wild West.
That's a good way of thinking of it.
I had a quick question, which is the most obvious type of very fast transient that we've recently discovered are these FRBs, where the rates are so high that you can be just staring at a small patch of sky and detect one. So my quick question was, I guess, if FRBs had a near infrared counterpart, we would detect a bunch of them, but they don't have that as of now. Do we think they have any?
As of now, yeah, as of now, there's nothing detected like in the optical and not in infrared, but there are theories of that, and those theories, be it inverse confidence scattering or whatever it is, all predict something that's quite faint and down to like, if it's in the AV magnitude, like 25th, 26th, depending on its distance and energy. So you need a very sensitive telescope to do that. So either they don't exist, or if these are right, then you would need something like Roman to find that.
Exciting.
Yeah.